Google Classroom, the link in Google Classroom for you. So today we're going to learn about electron configurations. You ready? You are going to need your resource packet, your periodic table, I suggest the one that you took notes on, and your notes.
This periodic table filled out for test.
Filled out like what?
Like the color, I know you posted it, or do we really even need this for our test?
Not for this test.
Okay. I just didn't know if I needed like 3 of these.
Hey, is it okay if my notes like get out of order from yesterday?
That's yours. I'm not looking at your notes. I'm just looking at your lab. No, she did her lab in All right, are we ready? Not really, but we feel like we should say yes. Okay, now I'll take it. I'm good with that. Starting all kinds of fun
Is anything else going to go on this one?
What?
Is anything else going to go on this one?
Okay, so let's see what we got here. Electron configuration. It's fine, I planned it that way. Hello. I do. Okay, thank you. Sierra, your mom dropped off a camera. It's in the office.
Can I get it, like, can I get it after class?
Yeah, yeah. Okay. Electron configurations show us the arrangement of electrons in an atom. That's what Bohr models do, though, right?
No, 60.
Kinda, ish. We are always going to write our electron configurations for a ground state atom. Okay? All the electrons will be in the lowest possible energy positions because it is in the ground state. However, before we can start actually writing electron configurations, there are a couple of rules we need to learn about because we use these rules to help us write the electron configurations. So we're going to go over each rule. The first one is the Aufbau principle. The second one is the Pauli exclusion principle. And the third one is Hund's rule. We're going to go over each of those. And then we're going to write some electron configurations, quantum numbers, and draw Bohr models. Would you like to join us?
Oh, no, to see what you do.
Not really much of anything.
Both might be great.
Oh. Okay, we ready?
One second.
Not yet, not yet. Yes.
What's the word?
Aufbau. We're going to go over each one of these individually and learn what the rule tells us, and then, like I said, we're going to write some electron configurations. So you're going to see these. You're going to see these again. So if you don't have them down yet, it's okay. You're going to see them on each of the next slides. Don't draw the diagram. Don't draw the diagram. But I will tell you that the Aufbau principle says that electrons will occupy the lowest energy atomic orbital available. Lowest energy atomic orbital available. So when we put electrons into these electron configurations, we're going to put them in so that the electrons are lowest in energy. Now remember, everything in our universe wants to move towards lower energy. So it would be silly for us to put it in a high energy state. We want to leave it in its lowest energy state possible. And we know that that's what happens naturally because of the atomic emission spectra that are generated when those electrons relax back down. We have something called degenerate orbitals. I'll talk about that in a moment. Okay, I'll talk about it now. Degenerate orbitals. The definition of degenerate orbitals is that they are orbitals that exist at the same energy level. They're orbitals that exist at the same energy level. So remember I said, well, Aufbau's principle, it's right here on the board, says that the electrons want to occupy the lowest possible energy positions. They want to be in the lowest energy atomic orbitals available. But we have some orbitals that exist at the same amount of energy as other orbitals. Those orbitals are called degenerate. They all have the same amount of energy. And I'm going to talk about this diagram right now because this is an energy diagram. And you can see we have increasing energy as we go up. So along the bottom are L values. That's just going to tell us the orbital set, S, P, D, and F. So here are our S orbitals. Here are our P orbitals. Here are our D orbitals. And here are the F orbitals. Okay? And this is just oriented so that we have them in order of energy. So the lowest possible energy orbital that we have is an S orbital, and it is in energy level 1. So this number here represents the energy level. That's our N value, the principal quantum number. Then we have the orbital right next to it. So in energy level 1, there is an S orbital. The next lowest energy orbital is it's an S orbital again. But it is in energy level 2. So we've gone from the innermost, closest to the nucleus, to the next layer. And it's still an S orbital because in the energy level 2, we have S orbitals. But we also have P orbitals. All right? So the next after 2S is 2P. P orbitals are a little bit higher in energy than S orbitals. But can you see 3 lines there? How many P orbitals are there? 3 of them. They're all at the same energy. They are degenerate orbitals. This is where your periodic tables come into play. Now remember we talked yesterday about how as we go from one position on the periodic table to the next, we're adding a proton in the nucleus and an electron somewhere outside of the nucleus. Do you remember that? So I just want to go through this real quick, or slower if we need to. If I start at element number 1, we have 1 electron from element number 1 and 1 electron from element number 2. What energy level is that?
1.
The first 2 elements on the periodic table, what energy level are they in?
1.
They're in energy level 1, and those electrons go in what type of orbital?
S.
Do we understand what I'm asking? These first 2 elements are in energy level 1. And remember we said we would move helium over here. They're both in the S block. So that goes in, both go in an S orbital. They go in the 1s orbital. It's energy level 1 and S orbital. Do you see this here? Energy level 1, S orbital. How many electrons can go in each atomic orbital? 2. So there have to be 2 electrons in that energy level, in that orbital. So we got to helium. Let's go down to the next row. Lithium and beryllium. Lithium and beryllium, what energy level are they in? Energy level 2. So the electrons that they're contributing are in energy level 2. And what type of orbital are those first 2 spots? 2s. 2 electrons go into that orbital. Let's continue with energy level 2. Boron through neon. How many, what type of orbital, what orbital set do those electrons go into? P. How many orbitals are there in the P orbital set?
6.
How many orbitals? 3. 3. How many total electrons can go into those orbitals? 6. Each atomic orbital gets 2 electrons. There are 3 atomic orbitals for a total of 6 electrons. Do you see these 3 lines? line corresponds to one of the atomic orbitals. Each line represents the 2 electrons that can go in that atomic orbital. So here are the 6. Now, here, that would be where we would see 6 electrons. It would be 2 for the first line, 2 for the second line, 2 for the third line. So, I told you that you should have your resource packets out. Do you remember this diagram that shows you all the orbitals? Do you see those p orbitals? There are 3 of them.
Yeah.
And remember we talked about the Sub-L value? Tells us about the orientation in space. It keeps them separate. This line represents -1. This line represents 0. This line represents +1. Do you see the connection? Okay, so that got us to neon. Now let's go to calcium. What energy level is calcium in? I'm sorry, potassium and calcium. I'm sorry, I skipped sodium and magnesium. Let's go to sodium and magnesium. What energy level are sodium and magnesium in? 3. Energy level 3. And those electrons are going to be in what type of orbital? S, because they're in the S block. Look what comes next. Zach?
So then the one line for the S is just 0.
The one line for the S is just 0. Yep. The Sub-L value is 0, yes. So after 3s, after we go through magnesium, now we have aluminum through argon. And the electrons contributed from aluminum through argon go in what type of orbital? P, right? Those are these elements over here. They're in the P block. Those electrons go into P orbitals. How many P orbitals are there? 3P.
What do you mean when you say how many like p orbitals are there? Like from this part?
1, 2, 3.
Or weren't there just 2 p orbitals?
There are 3 here.
Wait, so then the 2 below it, isn't that still part of P?
That's the energy level. Within each energy level are different sets of these orbitals. So in energy level 1, there's only an s orbital. And you look at where the elements are, those 2 elements, they're putting electrons into an s orbital. There's no p orbital. There's no elements that are in the p block in energy level 1. So each energy level can have, they start with s every time. They start with s. You can see we can count from 1 to 7 with s. There's always an s orbital. But they don't all have P, they don't all have D, they don't all have F. Okay? So let's keep going because I really want to get through zinc, at least. Potassium and calcium. What energy level? 4. Those electrons are going to go into what type of orbital? S. 4s is next. Then what happens? We hit scandium, scandium through zinc. What type of orbital do those go into? They go into d orbital. And what energy level are those d orbitals? 3d. Do you see it? Yes, Kara.
I understand the correlation, but can you go through the pattern on the diagram again?
The pattern. So like how this goes up like this.
Does it just move like that?
Yeah, we're literally looking like, okay, this is the lowest in energy, we're going up to the next one, this lowest in energy, we're going up to the next one, and next. So it is just going back and forth, and it does that because it's got it down here, we're graphing the L value.
Okay.
But we could smash all of this over here and just have them all just lined up like that.
Okay.
It's just splitting them out by energy, or by L value. Does that make sense? Okay. So, I want you to find, let's see, barium. Element 56, did you find it? Okay, element 56, barium, is what energy level? 6. And what orbital? S, so we're here, right? Then we're going to ignore 57, and we're going to go 58. Where's 58?
4. 5F up there.
It didn't go all the way up.
They just stopped.
Yeah, we just stopped. But you would have 5F, then, 5F, 6D, 7P, 8S. It would just keep going.
Wait, where'd you get 8F?
We don't have elements to fill those spots, but it would, based on this pattern, that would be what was next. Do you see the pattern? Do you see the connection?
Yeah.
Oh my gosh, right? All right, let's go on. The Pauli exclusion principle. Pauli exclusion principle. This is a scientist's name, Pauli. His name was Wolfgang Pauli. He's an Austrian physicist. And his exclusion principle is gonna help us out a little bit. We're gonna be able to make a connection here between this and the quantum numbers. We're not gonna do it quite yet, but I wanna point out that I've told you over and over, how many electrons can go in an atomic orbital?
2.
2. Each one of these lines represents an atomic orbital. So we're going to represent our arrows or our electrons as arrows, and the ones that are spin up are going to be an up arrow, and the ones that are spin down are going to be a down arrow. Okay? That's going to be important later on when we try to connect the quantum numbers to our diagrams. But I want you to see, Pauli's exclusion principle tells us that you can have a maximum of 2 electrons in every atomic orbital as long as they are opposite in spin. Opposite in spin means 1 up with 1 down. You can't have 2 up, you can't have 2 down, not in the same atomic orbital. So if we're looking at this top example here, what's the problem?
They're the same.
You have 2 arrows that are up into S, and that's not possible. The correct way to do it would be 1 up, 1 down. Okay? So, Pauli's exclusion principle says that whenever you have 2 electrons in an atomic orbital, you must have them, we call it spin paired, which means one's up and one's down. One's up, one's down. And up always comes first. Okay? We good with that one? And that brings us to Hund's rule. Okay? Hund's rule basically states that, okay, I'll just read it to you. A single electron with the same spin must occupy each equal energy orbital before additional electrons with opposite spins can occupy the same orbital. Don't write that down if it doesn't mean anything to you. Don't write it down. Seriously, don't write down things just because I have it up here on the board. Write it down in a way that makes sense. All that means is that when we have degenerate orbitals, see these degenerate orbitals right here, 2p? There are 3 orbitals, 3p orbitals, they're all the same energy. P, D, and F are all degenerate orbitals. P, D, and F are all degenerate orbitals. So anytime we have P, D, or F orbitals, we're going to put 1 electron in each orbital before any of them get 2.
So anytime we have P,
P, D, or F. I'm going to say that again. Anytime we have degenerate orbitals, which are P, D, and F. Anytime we have degenerate orbitals, which are P, D, and F. Every orbital gets 1 electron before any of them get 2. Okay? So if you look at the example that I have here, these p orbitals, they all have an up arrow, which would be incorrect if we did it this way. Pauli's exclusion principle tells us that they have to be spin paired, which they are here, but not every one of those orbitals has 1 electron in it. And there are 2 reasons for this. One of them is that when we put 2 electrons in an atomic orbital, they're closer to each other. And electrons repel each other. More repulsion means higher energy. So we can't do that. The other reason is, all of those p orbitals are the same amount of energy. And we already talked about how the Aufbau principle says we have to keep the electrons in the lowest possible energy states. So this one is way lower in energy than this one. This is the natural behavior of atoms in their ground state. They will put one in each atomic orbital because those are all the same energy, and this creates a repulsion that is higher in energy. How do we feel about that? Not really sure because we don't know what we have to do with it yet, right? It's like I'm one of you, right? Yeah? Okay. Oh man, isn't this fun? Not yet. Yes, Chase.
I don't understand anything you just said about repulsion.
Okay. So when two electrons are together, they're both negative charges, and negative charges repel each other. Does that make sense?
Like just two positive electrons, or just,
Electrons are always negative.
okay, so two negative, okay, they repel. Okay,
The
that
same charges, they repel each other. Whether it's positive or negative, they always repel.
okay.
So when we put them in the same atomic orbital, because remember, an atomic orbital is just a region of space. So if we put two electrons in that same region of space, they're going to repel each other. It's a smaller repulsion when the spins are paired, one up and one down, than if they're both the same, right? This is a smaller repulsion than this is, but they're still higher in energy because the electrons are too close together.
So if they're spinning opposite directions, it's smaller.
A little bit, yes. But this is still higher in energy than if we have one electron in this region of space, one electron in this region of space, and one electron in this region of space. Because they're not as close together, so they don't repel as much. Does that make more sense?
I think so.
Okay, Kara.
I don't think I was here when you guys talked about spins, is that just the direction of the orbit?
The spins, one's up, one's down, they're just spinning in opposite directions.
Okay.
Okay, so, are you ready? Because we haven't done any electron configuration discussion yet. Electron configuration discussion, that was a lot of shuns. Not, okay, all right. There are 3 forms of electron configurations, and you're gonna have to write them all. Yay!
So we're gonna write down that table.
You don't have to write down that table, no. Okay, so the first one is orbital notation electron configuration. That is a mouthful. Orbital notation is the arrows. That's what you need to remember. Orbital notation is the arrows. So remember I told you you needed your packet? Remember this picture up here with all the atomic orbitals on it? I want you to look right below it. There's an Aufbau diagram. See that? And that Aufbau diagram is basically one that includes all of the elements that we currently know of on the periodic table, except for 7p is not listed, but it would just be above 6d. That Aufbau diagram lists all of the orbitals with their energy levels in order of energy. The bottom is the lowest energy, the top is the highest energy. Yes?
What did you
Owen.
say the arrows were called again?
The orbital notation electron configuration, that's where we're going to use the arrows. Okay? So I draw your attention to the Aufbau diagram because you see those lines there with the 1s under it, the 2s under it, the 2p under it. All that we've done is we've taken this Aufbau diagram and we started with the lowest energy one, that's 1s, and we wrote it here, and then we went up to the next highest or the next lowest energy one and we wrote it right beside it. And we're just going to keep tracking our way up this diagram, writing them side by side by side. If we get to the end, we'll just start another row down beneath us, just like we would a sentence. Does everybody see that? Do we all see where that comes from?
I'm confused what you're talking about. Can we say that again?
Yeah, so in this Aufbau diagram, at the bottom, the lowest energy is 1s. Do you see that?
Yeah.
So there's 1s. The next one is 2s. We just write it right beside it. If we go up again, we get to 2p. We write it next door.
Why is there a space in between them?
They're just spread out so that we can draw our arrows. But see this 2p, there are 3 lines for 2p because they're degenerate orbitals. Each one of those lines represents an orbital. So we have to draw 3 lines for 2p, or for p in general. For p, how many lines are we gonna have to draw?
5,
And for f?
7.
7.
So for like, so it'd be like, for the S's, they each get 1. So after 3p or 2p, you'd go up to 1s and or 3s and it only have 1 line.
Yes. Then 3p, 4s, 3d will have 5 lines.
Yeah.
Yes, you
So
just
that's
keep
why
going up.
there's a line in between them.
Yeah. Yes, Tracy.
The arrow.
Don't worry about the arrows yet, we haven't talked about it. Ignore the arrows. Don't look at the arrows. Stop looking at the arrows. Okay, Owen, did you have a question?
Yeah.
Okay. Does anybody else have a question before we go on to the stop looking at the arrows? Yes, Owen.
Would you like us to keep all of the same, like, all the S's and all the P's together if you were to, like, have to draw these out?
When you draw them out, you have to do them in order of energy.
So the order of the thing that we have?
Yes. So they have to be in this order. It's gotta be 1s, 2s, 2p, 3s, 3d, 4s, 3d, blah, 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 blah. Got it? Okay. Now, let's talk about the arrows. Gracie, you can look at the arrows now. Let's talk about the arrows. The arrows represent the electrons. Each arrow is 1 electron. So how many electrons does lithium have?
3.
3. It's element number 3. It's got 3 electrons. There are 3 arrows. Got it? Now, I always want to get ahead of myself. Let me see if I can do this. Let's go ahead and do this. Chase, pick your favorite element up here.
Carbon.
Carbon. So I'm going to draw the Bohr model for carbon. If you want to practice drawing your Bohr model, go ahead and draw it. I'm going to draw one up here quickly so that we can talk about it. Okay? All right. So, we have how many electrons in energy level 1? 2. Energy level 1, 2 electrons. There's only an s orbital there. Okay? 1 up, 1 down. In energy level 2, how many electrons are there? There are 4. So this is where we have to go back to the periodic table. I want you all to look up here. I don't want you to look at yours. Mine matches yours. I don't want you to look at yours. I want you to look up here. So really what we're doing as we go from, or as we're trying to draw the electron configuration for any element, is we have to start at the beginning and we have to figure out where are the electrons to get us to our element of interest. Our element of interest is right here. So I'm going to go through hydrogen and helium. Those are 2 electrons in energy level 1, but in energy level 1, those are considered both in the s block. 1s. There are 2 electrons, 1 up, 1 down, because we have to use Pauli exclusion principle and the Hund's rule, okay, and the Aufbau principle. After we get here, we've got our 2 electrons. Now we're going to come down here. Now we're into energy level 2. How many electrons are in an s orbital here? 2 of them, right? Those are 2 elements in the p block, or I'm sorry, the s block. So we have to put 2 electrons in a 2s orbital. So here's our 2s orbital. 1 electron up, 1 electron down. Spin up, spin down. Then, we're still not at carbon. We have to do 2 more. Which block are those in? P block. And how many electrons are there? 2 electrons in the p block. Hund's rule says 1 in each p orbital before we get any orbital containing 2. There are 2 electrons for the p block, 2p.
How would there be 2 electrons in the P block because the P orbital has 6 electrons?
The maximum it can contain is 6. because boron contributes 1 and carbon contributes a second. Okay? Trust me, bear with me, okay? Now, how many total electrons do I have in my Bohr model in energy level 1? 2 electrons in energy level 1 of my Bohr model, 2 electrons in energy level 1 of my electron configuration. How many electrons do I have in energy level 2 of my Bohr model? 4. 4 electrons in energy level 2 of my electron configuration. Do we see it? All right. I'm going to go on to the next form of the electron configuration, but they all contain the same information. It's just a different way of writing it. This one's called the electron configuration notation. And it really is truly just a condensed version. Instead of having a line and drawing arrows, we condense it and we indicate how many electrons using this superscript number. So for krypton, we've got 36 electrons. Krypton. Where am I at? Does that add up to 36? I think so. That's my Bohr model for krypton. How many electrons do I have in energy level 1? 2. That little red 2 right there indicates that I have 2 electrons in energy level 1. But in energy level 2, I don't just have s orbitals, I have s and p. So I've got to separate them and indicate it. All we've done is we've taken the Aufbau diagram, the orbital notation that we just had, where they were all in order. They're still in the same order. We just got rid of the lines, got rid of the arrows, and we've taken those degenerate orbitals and we've combined them. So now I have 2s2, 2p, 6. I have a total of 8 electrons in energy level 2. Does that match my Bohr model? So then in energy level 3, it says I have 18 electrons over there. How many electrons do I have in energy level 3 for my electron configuration? We've got 3s is 2. I've got 3p, that's 6, that's 2 plus 6 is 8. But look over here. 3d, there are 10 in there. So 8 plus 10 is 18, so that matches what I have over here. Now see, remember what we said, it goes 4s and then 3d.
So you have to like skip a space and then go, like, cause you're in energy level 3, but you put a 4s in between them. So you have to like skip a spot before they add up.
So if you look at the the Aufbau diagram here, you have to go in order. 1s, 2s, 2p, 3s, 3p, 4s, 3d.
Wait, 4. I was looking at like the, but I guess they're in the same line.
4s are these two, then you get to
Yeah,
scandium,
that's
which
what
is 3d,
Yeah.
and then 4p.
I was confused on the different energy levels.
Chase?
So is this how they made the periodic table?
No, the periodic table was made before this. Remember, this is in the 1900s. Periodic table was well before that with Dmitry Mendeleev.
But like,
1800s, right? Henry Moseley rearranged it, but this came about after that.
I just don't understand how they can know all the electrons and all like the levels and everything all the way back then, where it works with the table.
They didn't know.
So then how's it work?
It just happens.
See, that's crazy.
Too much of a coincidence?
See, this
Yeah.
is why I don't
That
like
would-
this. But
We're
this
not
just
even
don't make
halfway through the
sense.
first quarter. How could you not like
It would
chemistry?
make sense if it was like on purpose, but like it just happened, and it's like they don't know.
Yeah.
I don't like that.
Okay, do you have questions about this form? Yes, Bridget. I'm I'm sorry, what? I can't hear you over this.
Something about the arrow.
I heard arrows, that's it.
Going through, can we go through it, like the process of finding the?
We're going to. I have some examples after this. I just want to talk about all three forms because I'm going to have you write all three forms. Okay? All right. One more form. I lied. Don't do that. Okay. Here's our last form. It's the noble gas notation. Noble gas notation. Yes.
You wanna start all that?
No. 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 Don't look at it. All right, noble gas notation. So let me change this. And let's see. I want to use. Let's do strontium again. 38. Is that right? There's my Bohr model for strontium. So if I want to write the electron configuration in this notation for strontium, I'm going to point it out to you so you see it. I see it, but I don't know that you guys always do. So if I look at this, I see a full shell right there. Do you see that 8 electrons? That's a full shell. And we just did this one. So what is that? What element does this inner shell represent? This represents krypton. So instead of writing out blah, 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 we can write out the core and then what's left over.
So basically up until the full valence shell and then the leftover.
Yeah, so for strontium, I don't need to put a period there, that makes it senior, that's weird. I'm going to put in brackets the symbol for the core, right? These 36 electrons right here, those are krypton. So I have a krypton core, and then one outer layer. How many electrons are in that outer layer? 2. And what is that layer? What energy level? 1, 2, 3, 4, 5. And what orbital are those in? S. And how many? There you go.
How do you know it's in US orbital?
Because strontium is right here. And those 2 electrons that are beyond krypton are in the S block. And it's 2 electrons beyond krypton. So let me restate that so everybody heard me. The inner core represents krypton. Those 36 elements, or those 36 electrons right there represent krypton. I have 2 beyond that. Krypton is an energy level 4 at the end. So when I come back down, I'm going to go through cesium and I'm sorry, down row. Rubidium and strontium. Those elements are in energy level 5 in the S block. So I know that these 2 electrons are in 5s.
So a way to like think about that is it like up the element up until like the full valence shell and then the extra?
What you're looking for is the highest number with P6. So that's what's indicated here. The highest number with P6 is 2. So that's going to be a core of something, right? Because we have 6 columns in our P block. And these are noble gases. This is the noble gas notation because we are using our noble gas as a core.
So highest gas.
Highest number that ends in P6. So if we were looking at iodine, now let's look at nickel. See, here's the electron configuration notation for nickel. 1s2, 2s2, 2p6. So there's a p6. 3s2, 3p6. That's higher. 4s2, 3d8. Here's my highest number with a p6. So this represents a core. I just have to go to energy level 3. Energy level 3, where I have p6. Well, that means I'm going to be 1, 2, 3, 4, 5, 6 right here. That's argon. So argon is my noble gas, and I write everything that comes after it.
So you go to the highest P6 and then you go over however many elements, like it says.
Mhm. Each one of these electrons represents a spot on the periodic table.
Wait, so do you always go over 6?
Right, because noble gases, we have to go P1 through 6 to get to that last column. The last column is the noble gas. Okay? Yes, Bridget?
Sorry, you have to use the, what are the numbers called that are like higher up? Like the little numbers.
Oh, the superscripts?
Yeah, you have to use those to know how many elements you're going over to find.
You can. So if I were to give you this one and ask you to identify the element, you can count these out. 2, 4, plus 6 is 10, plus 2 is 12, plus 1 is 13. What is element 13? It's aluminum.
Aluminum.
Wait, did you count like
The superscripts, these, they're like experts, yes.
I know what's going on.
Yes, go ahead. Yes, Owen.
So remember, it's krypton in the blue example, the 5s, superscript 2 would be red.
So I guess you guys get away with not having homework this weekend.
This is so exciting.
To not have homework,
I know.
or to understand electron configuration.
Just put it
Oh.
on. Do you have to put yours on?
I was counting down the seconds, I told you you would have time.
You guys have to